Hi, so my name is Mark Procos. I'm the General Manager of United Parachute Technologies. We are the largest container manufacturer in the world. And AADs, I don't know how much it's an issue here, but in the US there's been a lot of issues on compatibility of AADs with containers. So this is something this talk I've done a couple of times. I'm a little bit rusty, so excuse me. My videos might not work with the PC. I run on a Mac and they don't have the adapters for me. Okay, so I'm just going to go into a bit of the background. Okay, the advent of the modern AED. The first, the first electronic AEDs on the market, besides there was the Sentinel, but the commonly used one that we use now is the Cypress, the Vigil, there's a Mars now, and I believe there's two others in the market that are in the process of getting there. So it's a market that's expanding. When they came on the market, it was a large learning curve for container manufacturers, canopy manufacturers, and the AED manufacturers as well. So through trial and error, we saw a lot of problems. The first AEDs came out, they were opening high, things were not as reliable as we liked them to do. But right now, I think the AEDs on the market, they're all pretty good. They're all doing the job and they're saving people when they can. Okay, in the beginning, when these things first came on the market, so Helmut was the first guy with the Cypress, and he contacted all the container manufacturers and said, send me a container, and I'll figure out how to put this thing in your container. That was great. These guys are electronic geniuses. They don't manufacture containers. So there were a couple of issues in the beginning where they placed the cutter and so on. So the next step, if you look at the history of what's happening recently in the sport, to date there's about 20 plus fatalities where an AED fired and the person, and it failed, whatever, the equipment failed to save the person. A lot of these people went in at line stretch. So they're developing canopy. I don't know if you guys have been following this in forums and in the news, but there's a lot of cases where these guys went in, if they had maybe 100, 150 more feet, would they have survived? Possibly, most probably. So all the AEDs activated, and did these AEDs activate at the correct altitude? Us as container manufacturers, that was the first question you asked. How do we know that this is accurate? The AED manufacturer said to us, your equipment isn't opening fast enough or quick enough. So this started a conflict within the industry, and still an ongoing conflict. Oh, I've got to find the right button, sorry. Okay, so let's look at why we believe, or why we're looking into this. We don't have all the answers, but we are looking. So the first thing we obviously find out, is the AED activation the correct altitude? This is a calculated altitude based on air pressure and speed and so on. But because of our body position, the AED fires at a virtual altitude much higher than the actual firing altitude. So in other words, when you're on your belly, you have this low pressure system on your back where your AED sits. So the obvious thing is put the AED in the front and then we can use real altitudes, but we can't. So we have this virtual thing. So for instance, I know the visual firing altitude is 1,100 feet. That's the actual firing altitude, but the published altitude is 850 feet. So they guesstimate that the burble on our back is around about 260 feet. All the AED manufacturers work in the same thing. So why is this? The faster you go, the bigger the burble, the bigger the variation from the front to the back, the high pressure on the front and the low pressure on the back. You guys can stop me if you have questions, if you don't understand this. Sometimes it's confusing for me even when I look at this stuff, when I'm looking at graphs and so on. Okay, so that was the one thing. Is the AED firing at the right altitude? We don't know that. These AED manufacturers aren't going to give us the inner workings of their AED. This is their power, their knowledge, their algorithms are what makes their product successful or not successful. So they're very reluctant to give the stuff to us. So we can't test that. We rely on them to test that kind of thing. Could it be delayed reserve pilot chutes? And we'll look at a lot of these things later. Or, for that matter, delayed reserve openings. all equipment is tested. When we test equipment, it's pretty much in ideal conditions. We have our riggers packet, we take it, we put on a dummy, we throw it out of the plane. If that works well, then we put on a real jumper. Sometimes a dummy too, but he's a real jumper. He actually walks and talks. And so our test jumpers will carry on. They'll test the equipment for us and determine that this equipment is fairly safe. But normally on fresh reserve pack, there are things in the TSO that require us to stress the pack job, put it under pressure, heat and cold and so on. But it is really an ideal situation. And if you do 100 test drops to certify to TSO equipment, that's a lot. We don't even get that much. That equipment, the first month we put it on the market is going to have more jumps than that. So we can only get, our testing only gives us reasonable assurance that this equipment is going to work to the best of its ability. Okay, the longer you're in business, the better you have a better data and you're more reliable. The other thing is the AD manufacturers. Well, the modern rigs are more compact. I see some older people here, so they most probably were jumping Wonder Hogs and Spring Hogs and all the old equipment that was around. Imagine trying to jump with that equipment and go free flying or sit flying for that matter. You'll have shit coming out everywhere. So, just through necessity, our equipment has got more compact, more streamlined, tighter, and we've learned stuff along the ways as well. We realized that we had to start staging our reserve deployment, and I'll get into reserve deployment later. So now we have what we call dynamic corners on our main containers as well as our reserve containers. So in other words, it traps the reserve bag in there till the pilot chute starts doing his work. In the old days, what could happen if a person was on his back or cutting away from malfunction, not quite stable, there were cases where the reserve bag would leave before the pilot chute. The pilot chute might hesitate, caught in his burble or caught around an arm or leg, and that reserve bag would be out there, which is catastrophic. There were some fatalities in the late 80s with equipment like that. So from there we learned that we added dynamic corners to our reserve container. I think every modern rig on the market has dynamic corners or some method to keep the reserve bag in till the pilot chute starts doing its job. Okay, so we looked at all of that. Now let's go back to see what is required. AD's manufacturers, first thing said, your reserve has to open in 300 feet from your reserve activation to a fully flying, survivable, so-called survivable landing. The other side of the other side says 3 seconds. 3 seconds 20 years ago is a lot different to 3 seconds nowadays with the equipment we wear in, the speeds we fly and so on. And that is a common misunderstanding that people have, that a reserve opens in 300 feet, or 3 seconds for that matter. In real life they don't. So let's look at the truth. I'm not going to go too much. This is from TS 135, which is the latest TSO standard we have. It's TSOF. C23F. Okay, so I won't go too much. I'll give a basic explanation of there is a minimum standard of 3 seconds of 300 feet, but that's for an average jumper. As you go higher in weight or higher in speed, so you have to determine when you test the equipment what's your maximum pack opening speed and also the weight of your equipment. So I'll go to the next one. So basically what it says is, as you go heavier or faster, your reserve is allowed to take longer to open, and as you go heavier, you're allowed more distance for your reserve to open. So the 3 seconds at 300 feet is just a baseline. It is not what modern equipment does. Imagine you're on your head and your reserve opens in 3 seconds if you're free flying. You must probably break every bone in your body if your equipment doesn't come off you. So if you look at a typical reserve deployment, and I'm going to get to some of them later. Okay, so let's look at the stages of where we have to deal with, the stages of deployment. I'm going to go into the one. We have the activation of the reserve, what's going to start this thing moving. The PC launch, bridle extension, bag extraction, line stretch, canopy, out of the bag, and then the final reserve inflation. We have to get all of that in the required time for the TSO. So 3 seconds or 300 feet is a baseline, and then it gets longer and further as you go up in speed and weight. So let's look at how we activate the reserve. Every container on the market, I don't think anyone is designed specifically to work with an AAD. The AAD was an add-on, and it's still an add-on if you look at the design, container design. So the activation first form of activation what everyone tests to. Very few manufacturers nowadays actually go out and test in any. They'll go out, the jumper jumps out, and they'll activate the reserve. If we're doing heavy drops, we will we have a static line to the reserve. So reserve pilot chute, that's an ideal way for a reserve pilot chute to get out. You pull your reserve handle, your pilot chute leaves. And as I said, all container design. So now when we add it, and sorry, the next one is the RSL. Okay, so you cut away, your RSL activates your reserve. It's the same mechanics as a reserve ripcord. Then AADs were added. Now we've got to put this cutter, and now the order of the opening has changed. When you pull a reserve pin out, it's coming out the top, the loop gets left in the container. Some containers, you pull the loop through like a racer and so on, the pop-top type things. So the AD cuts somewhere from the top of the pilot down to the base of the pilot chute, along the closing leaf, from the top of the PC all the way to the base on some containers, like racers, javelins, for instance. And then you get Mirages, they on the top. Ours is below the pilot chute on the kicker plate, and they're anywhere in between there, depending on the container design. And the last one is a mod. The mod isn't in effect for this, because the mod actually main activated reserve deployment system like the Skyhook and Sky Anchor. There's other names out there, I don't know them all. But that actually pulls the reserve out the bag, so you can get better than the 3 seconds or 300 feet. So let's look at the pilot chute launch. Okay, first of all, there's different kinds of pilot chutes and different methods in container design. We have the internal pilot chute, like our system, the Vector, and the Aerodyne rig, the Mirage. Our pilot chute is encased inside the container under multiple flaps. Well, we have to make sure with the internal pilot chute, there's always room for that pilot chute. Depending on the size of the pilot chute the container manufacturer is using, we have to make sure there's enough room for launch. So in other words, we can't make our corners too closed in. It can restrict the pilot chute. The flaps have to be easily moved out of the way. I think one manufacturer, I don't know if I'm not going to mention their name, they decided they wanted to use springs to release the flaps so the pilot chute could leave. Well, the springs kept the flaps closed, so it didn't work too well. They had to remove those. There was an AD out on that. The other one's the external pilot chute, javelin style rigs. What's the one here? Teardrop, sorry. And the racer. So they work at different dynamics. So the external pilot chute, the theory is that this thing doesn't have flaps to move out of the way. So then we look at, I should have reversed that order. So we look at spring sets. All internal pilot chutes, they have around about 40 to 50 pounds of pressure. So that pilot chute, if you compress it down to 1 inch, is going to generate about 50 pounds of pressure. If you look at the external pilot chute, you can't do that. Because the external pilot chute is on the top, at what it points loads the pin. In other words, all the pressure of that spring is pushing against the pin. So they can't use a 45-pound spring, because that's going to be very difficult for you to pull the reserve ripcord. You have to do it in 20-odd pounds. So they have to use a weaker spring. Not that these pilot chutes can't launch, because one's got a stronger spring and will launch further than the other. The reality is in freefall, when we look at videos of pilot chutes launching, most of the time they jump up and fall straight on the jumper's back. The burble effect, there's no pilot chute in the market that can really punch through a burble. You know, manufacturers can claim all this. We use different methods of getting the pilot chute to the end of the bridle. So spring strength is not really an issue. It's just a method of doing it. It's just a different design. But burble is something that we have to deal with. So that comes into, pilot chute design. Okay, how do we clear the burble? So our pilot chute is a solid pilot chute. It has no mesh. It has pros and cons to that. It has no mesh, but what happens is, doesn't matter how it hits a wind, it can generate lift to get to the end of the bridle to start doing its work. That at low speeds might be not pulling as much, but what is not a lot of force to pull doesn't mean it's not enough. All the pilot chute has to do is get the bag out of the container, the reserve bag. So different methods. Some guys use big hole mesh. Some guys use different style of mesh to try to get a bit of lift if the pilot chute's lying on its side. And some use balance springs, some don't use balance springs. There's a theory out there, the pilot chute starts moving, if it's balanced, it's not going to spin as fast. If it's unbalanced, it can end up on its top. If the top of the pilot chute's heavier, that's going to go down. Gravity's going to do its work. So the type of pilot chute, we got to clear the burble, we got to get the bridle to a full extension. The quickest way we can do that, we believe, is by getting our pilot chute to doesn't matter what direction it's facing, will create enough drag. Once it gets to the end of the bridle, now it can do its job. No pilot chute can do anything when it's flying around in the air without any tension on the bridle. Okay, so bag extraction. So yeah, we come into the type of pilot chute. Some pilot chutes are going to create more drag than others. Depending on the container design, you might decide to have a weaker drag coefficient than a stronger one. The thing is, to get the bag out, you just have to have enough force. So there has to be enough room for the bag to get out as well, so the dynamic corners can't be that close. And sorry, I'll talk about dynamic corners. That's when the container actually goes over the top of the bag to some degree. So we have to make sure there is room for extraction. Some containers have more dynamic corners, more percentage of the bag covered by their flaps or the corners. Some have less, depending on the strength of their pilot chute, or when I say the strength of the pilot, the drag coefficient of their pilot chute. And that creates the timing thing. So you get your bridle out, you start creating drag, and now your bag's hanging there and it'll pull out. I don't think there's any container out there that will hesitate at this stage. Most containers nowadays on the market have sufficient drag to do that kind of job. This was one of the things that PIA started discussing, to say, well, maybe this is happening with these AADs. Maybe that's what's happening. The dynamic corners, these tight rigs are not allowing the bag to leave the container. And that's what the AAD manufacturers came to us with. Is this the truth? Does this happen? So PIA created a series of tests. So every container manufacturer that's part of PIA is doing this. Every time we get a reserve in for a repack, we put a scale on it, we've got a digital scale, and we pull the bag out the container, and making sure that we're not getting excessive forces that is going to worry us about our bag leaving the container. So far I know that 3 manufacturers are diligently doing this. So the rest of the others, some of them don't believe they have a problem, or some don't want to deal with it. Okay, so is it too tight or too loose? We watch that. We have found that in our containers that we found that we don't have, so far we haven't found a problem. There's 1 or 2 cases where we found that there was really high extraction forces, and when I say really high, it still would have worked, but it was higher than we like. And it's because somebody had put a container that was way too big for, a reserve that was way too big for the container. So follow your manufacturer's instructions about canopy compatibility with containers. Okay, line extension. So when we look at line extension, once the bag leaves the container, it becomes part of the whole system, and it creates drag itself. The bag itself is out there, the lines create drag. We have actually, when we were testing some of our equipment, we had a horseshoe malfunction with one of our dummies, and when we looked at the video, the lines created enough drag to launch the canopy. So all that's out there creates a certain amount of drag. So once the pilot chute pulls the bag out of the container, now that sets the sequencing mode, and there's inertia, so it's the initial pull that counts. When that pilot chute yanks that bag out the container, and it does with a lot of force when you look at these videos, that creates inertia that's going to help deploy the canopy, and also that bag itself creates a certain amount of drag. So where you place your lines on your reserve bag makes a difference to how it flies through there. So if we have it slightly offset, we feel our bag creates a little bit more drag. Okay, again, time is a problem. So let's look at canopy out of the bag. So we're in the process of redesigning our reserve bag. Our reserve bag worked really well in previous generations where free fall speeds were not nearly as high, people wore baggy suits. But now, with the advent of high-speed cameras and much better test equipment, we're starting to see that the amount of drag created is the canopy starts falling out the side of the bag. So we're looking at a completely encapsulated reserve bag. This is going to stop that happening. So you always want to keep your sequencing happening. So your reserve bag has to contain the canopy well enough and keep everything together till you get to full line stretch. And if you speak to the PD guys, they'll tell you what happens when your canopy starts coming out of the bag before you get to full line stretch. And if you jumped, you must probably felt it sometime in your career when you've had canopy dump or line dump out of a container. They hurt. Okay, so it may not hesitate, and it has to be secure enough to contain all the things and sequence the timing so nothing gets ahead of anything else. Okay, and then the fine thing is the canopy inflation. So that's up to the canopy manufacturers. We don't look too closely at it. When canopy manufacturers come out with new reserve canopies, we like to drop them just to make sure we're still within our TSO time frame. We always try. When we test, we don't worry too much about the extended time and distance. We like all our test drops because we know once it leaves, it's not a perfect world. So we like to test to 3 seconds and 300 feet, even though it's not a requirement. So now canopy manufacturers are dealing with these higher speeds. The latest reserve canopy on the market that I know of is the PDOP Reserve, really nice. I got one as soon as they came out. They don't necessarily open slower, but they open softer. So to open softer, they must probably drag through the air a little bit longer than the other one, but they still open in a reasonable time. They meet the TSO requirements. I mean, I was involved with some of their test drops. We managed to see them. So we know these canopies work. But all of this adds to that time. You know, maybe when if we look at most of our test drops, our reserves come out the reserves are fully deployed between 2 and 2.5 seconds most times. But when you jump with OP reserve, it's closer to the other end of it. So that little bit of time is distance. Okay, so what is the real problem? Why are these people going in at line stretch? So we've got to look at it. So AEDs are, as they were introduced in the 80s. Skydiving discipline has changed a lot. I started jumping in 1986. Actually, my first jump was 1982, but that was in the military. My brother's been skydiving since 1979. He used to have this big suit that used to inflate when he jumped out. So the speeds we fall at have got a lot longer. Now, AEDs have a reaction time. And I can't, sorry, I've got a little bit lost here. I just want to see something. Okay, so since then things have changed a lot. We're falling a lot faster. Skydiving disciplines have changed. Our canopies have changed. The technology in the canopies have changed. And now we see most of these cases that I've looked at, these people that went in at line stretch, they're all in the worst case scenario. A lot of them were tracking away from the dive. Most of them were belly to earth. So belly to earth, your AED is going to open at the lowest possible altitude that it's set for. Because now you've got to take into account that burble. If you're on your back, your real altitude is going to be higher when you open up. So all of these that I looked at, they were mostly belly to earth. The girl in California, she was tracking away from a jump, and I can't remember all the others, but that's the one that got a lot of media attention because she sued the company. Okay. So what is the problem? Is it our container design? Or is it the AED activation altitude? Should they be higher? Some AEDs open higher and have less of these fatalities. So there is a direct correlation. The higher you open, the better it is for you. You've got more time to survive. Is that the answer? No, it might not be the answer. The logic in you can't have it too high because you're going to have two out. And if we start moving them, start pushing them higher and higher, now you're going to have people having two outs the whole time. That could be, then we might be seeing a lot more fatalities with that situation. So if you do want them higher, now they can be set higher. I think every AED on the market now can be set to a higher firing altitude. Be careful when you do that. You've got to give yourself at least 1,000 feet before your known canopy flying and open to your AED activation. That will normally give you enough time to deal with any problems. So if your AED activates, and look at the high altitude, the visual 1,100 feet, and the Cypress is about 1,000 feet, I think. I'm not too sure on the M2, the Mars system. So if you push that up, you've got to put and you're not your opening altitude, your stable flying canopy altitude should be at least 1,000 foot above that. Okay, this is a typical light chase. This is from a visual. They give us the grass, which is great, so we can see what happened. And if we look at this jump, and why does it look upside down? Okay. So they exited just over 12,500 feet. The green line is the altitude line. The red line is the speed line. The yellow line in between is just a smooth speed. So the red line is taken every 1/8 of a second, and that's the speed it's registered. So that's what a graph looks like. Now they got a fixed altitude for the difference between belly to earth and the activation altitude. So there's a lot of fluctuations there. Now each AED has a different way of dealing with those fluctuations in their algorithm on how they smooth that out to try and get a real altitude or as close to the real altitude as possible. Well, on this jump, the guy went out. All those big spikes are normally caused by somebody going onto his back to belly. He might have been doing some free flying, but then he got to coming close to pull time, and this was a student, if I'm not mistaken, got close to pull time, and things got really out of control. So at this point is, where's the activation? Sorry, there it is there. Is that the activation there? Yeah. So now, this was a normal one, no problem, the guy was okay. But let's look at the next one. This was, have I got it? Yeah, this was a jump that happened in DeLand. It was a 250-pound guy. He hadn't jumped for about 20 years and came back skydiving. And I was at the drop zone when this happened. So the guy exited, then he tracked off. At track off time, he started having problems. The AED, so in the track, he's got now the biggest burble he could possibly happen. So I would imagine that 260 feet is a lot bigger than if he was just flying belly stable to earth. So this AED fired at, where's the altitude there? Have I lost it? No. So this AED fired at just about 1,100 feet. So this green line's the activation, just 1,100 feet. Virtual altitude. This is not real altitude. So we don't know if he has at 1,100 feet or 900 feet or 1,000 feet because we can't tell that. There's no way that we can tell that unless we have some kind of real instrumentation on the guy. So then you see the thing. He starts slowing down. The AED fires. He starts slowing down. He gets down below the activation speed because that's when it says the free fall open. And when we look at that altitude there, this guy was at his end of free fall was 74 feet. So at 74 feet, from 1,000 feet is when his reserve finally slowed him down below that speed, and he was over trees, and he just cleared the trees with his feet before he landed. We immediately took this and said, oh shit, our container took too long to open. But then we look at the activation, from the activation to the time. He's well within the we took it to performance design. It was a performance design canopy, and we said, is this normal? Bill Coe looked at it and says, yes. For that weight and that speed, this was a reasonable opening. It wouldn't meet the TSO standards. But the thing that happened, fired 1,100 feet and opened by 75 feet. Now the 75 feet is a real altitude because now the guy's standing upright. So that's a really close call. If that was any of the other two AEDs on the market, this guy would have been dead. As it is, he just broke a leg. Because as I said, 75 feet was when he dropped below the activation speed, which is, how many meters per second?
150 feet.
Yeah. 150 feet per second. So he had not slowed down completely. So this started scaring us. So we as a company, what we're doing to try make this problem end. We're looking at our extraction forces. How much does it take, as I said earlier on, how much does it take to get the bag out of the container? We also look at pilot chute efficiency. Is the pilot chute that we use sufficient to get that bag and the lines all the way to line stretch and open the reserve in a reasonable time? And then we look at total drag of the system. One of our engineers came up with a very cool system. And I have a video of me, and I don't know if the video is going to work because Wait, that didn't work. No. Yeah, I didn't expect the video to work. But anyway, what we've done, we've designed these one of our engineers, sorry, my stuff was on a Mac, and we've gone to the dark ages. I have to beat with a brick on this thing to make it work. Okay, so what we did, one of our engineers came up with the design for a load cell that's about this long, about that wide, and about half an inch thick. And we can put these in line anywhere in the system. So what we've done, we've put one at the base of the bridle where it joins the reserve bag. So we can now see, as that pilot chute launches, initial shock force, which we get peak forces of up to about 400 pounds, which is pretty incredible. And then we can see the sustained drag of that system there. We also got them on the risers, so we can see the total drag of the system. So what you'll see when a typical launch is that the pilot chute will go, you'll get a really high peak force of anywhere about 400 pounds, but it's probably the real because it's a peak force is about 120 to 130 pounds. And then you'll see that will drop off as the inertia goes, the system carries on going, and then we can see when the lines start loading and how much, and we've got one on each riser, so we can see how the lines are pulling on this and what the total force of the system is. So we can calculate how efficient the pilot chute is, how much the bag is dragging, because we minus that the force of the load cell on the bag from the force on the riser, and we can get a pretty good accurate. So we're looking at that, and when I presented this to PIA, and I'll get into what PIA is doing, Parachute Industry Association. Okay, so the industry at PIA, when we started discussing this, I'm a member of PIA, I'm the vice president, I'm also on the technical committee and the standards committee, so we're looking at that. So the industry standards are, what they are there. We have TS120. TS120 is a test protocol for AADs before they come onto the market. It's a very old protocol written by one company because they were the only company in the market then. TS120, we are trying to revise it. It's very difficult to get competing manufacturers to work together to actually come up with a new standard for AADs. The other thing that is TS112. So when this all started happening, the initial thing was the pilot chutes aren't leaving the container. They're too tight. And that was one of the AAD manufacturers told us that. Your containers are too tight. Your pilot chutes aren't leaving. So TS112 was a standard that was set up that tests the launch of the pilot chute. So what we do is we take 3 reserve loop lengths. There's the ideal length, the short length, and a long length, and we activate the reserves with cutter. And then the pilot chute and bag extraction force. Now I can show you what the TS112 test look like. So and maybe this might play. I don't think so, but let me try. It's going to play. No. Huh?
It's got the slideshow, jump back one slide, and then click the red.
Oh, wait, I can see this. Okay, so what TS112 is. So what we've got here, this is what we do, this is how we do TS112. This is one of our smaller containers, one of the microns. We have an AAD cutter in place. We've got the AAD in the container, and we fire it manually. As it fires, you'll see that a light comes on over here. So that tells us when the cutter receives the signal to fire. And then we time it from that fire to the pilot chute launch. Because before, the only way we could see it was by looking. When you saw the pilot chute, it came out, but we never actually knew when the AAD fired. So let me see this. Wait, come back here.
Three, two, one.
Okay, so we do this with every container size and every new AAD that comes on the market. They supply us with 48 cutters, and we do 48 of these tests. So we've done it for all the three common ones on the market so far. And through this, and a lot of manufacturers are doing this. I think all the US manufacturers have done this. There haven't been any failures. But this does two things. It doesn't only tell us that our pilot chute's leaving, it also tells us where we put the AAD cutter. Is it in the right position? Because there's been a trend to move that cutter higher and higher and higher in the pack job to try get to be as close to a reserve ripcord activation as they can possibly be. but we found other problems with that. As it gets higher in the pack job, there's more strain and stress on the cutter, and we've seen cutters are breaking, getting sharp edges and so on. Okay. Well, the rest of my slides did not copy over. That's not mine. So the next thing that's happening now is PIA, and our company, because of our development of these load cells, PIA has given us a budget to test every container on the market. So what we're doing now is we're doing a series of test jumps, and they're actually happening right now. The whole report's going to be completed by the PIA symposium. So we're doing a series of tests. And these are always live jumpers. We're doing a hop and pop. We're doing a 60 mile an hour reserve deployment with a ripcord. We're doing it with a AED cutter as well, a manually activated AED cutter. So as they get out, they wait, they count, they look at their speed, and then they fire the cutter. And this stuff is all videoed. So we've seen initially, okay, at subterminal, all these pilot chutes leaving all right. Subterminal has generally not been a problem. All these fatalities have been at terminal because of the speed. We also, on each of those series of jumps, we're actually taking an AED, adjusting the altitude, so the AED's actual altitude can activate the cutter, not manually cut it. Then we're doing the same test at terminal, and we got the load cells on all the pilot chutes and all the risers, so we can see what kind of forces. This is just for us as an industry to see that are the containers and reserve pilot chutes and bags a problem? And if that's the case, then we've got to adjust our design. But so far, we've done all these tests on our container. We haven't found any problems. Not that we aren't going to find any problems through this series of tests, but that's hopefully what we're going to do. And then we're doing the cutaway. So we'll be cutting away and letting the RSL deploy the reserve, and again, looking at the drag and that. So this report is going to be a public report. So if you go to PIA's website after end of March this year, you must probably be able to read the report. We're not using specific container names. It'll be container A, B, C, D, and E, and we'll have the report. We don't want it to be a marketing thing. We want this to be a factual thing for jumpers to be more aware of how AEDs activate, how ripcords activate, and what the typical loss of altitude and so on is. The other thing I mentioned about AEDs that I forgot to, this timing thing. Our AEDs give the signal to the cutter to cut. There's different methods of doing that, and that's something we still don't know. I know of the one AED, how they work. They have a charge capacitor that as it reaches the altitude, the capacitor fires the cutter. So we know that's pretty instant, and I've done what is the time on that? How many milliseconds? 2 milliseconds. There's some other AED on the market that the signal to cut actually charges the capacitor. The capacitor then cuts gives the signal to fire. So all these things take time, and the faster we go, the more chance that we're going to be at a lower altitude than we expect to be at the end of the day. So the whole thing, my whole presentation is what was the point of this? You need to know your equipment. We need to, as manufacturers, understand the equipment, and we know there's a problem in the industry, and then we are addressing it. Do you have any questions?
You must know the drag of the pilot chute, the maximum force that it produces.
Yeah.
So what is the percentage tolerance of the extraction force allowed to be of that pilot chute?
It has to be sufficient. Okay, and the real thing, the drag coefficient, people put out drag coefficient numbers. What does that mean? It doesn't mean anything unless you got the other end of the equation, which is a container. So all we want to see is that there's no hesitation at the worst case scenario is from a cutaway and an instant pilot chute from an RSL. So that's most probably the worst case scenario. You're very slow speeds, but you have a main out when you cut away. The other thing is maybe short delays could be a problem. So that's when you still got your, and you have to fire reserve, you still got your main in your container. That, from a container manufacturer's test point, is our toughest test to get out. So, example, we're now making a really, really small rig for girls. Well, it doesn't have to be a girl, guy can jump it if they want. But we're trying to get this container small. Well, when we narrow it down, our pilot chute as a percentage of the whole reserve pack job got too big. So we started seeing that this was, as it was leaving, the flaps were dragging. And we started seeing at real low speeds, we'd see the pilot chute grab, the bridle shake, and then it would leave. And I'm talking less than a tenth of a second, but it was something we'd never seen before. So we had to go back to the design board and we designed a new pilot chute specifically for that tiny container. And it's going to be a range of containers as well. So we can look at numbers all we want and calculate numbers. We want to see what the drag is so we have an understanding, so when we see numbers we can correlate it to what's actually happening in reality. But with any container design or canopy design or AD design for that matter, it's not what you do in-house, in an office or in the engineering department that really is the question. It's how does this react in real life? Because when we put pilot chutes in wind tunnels, we got these whole bunch of numbers. Yeah, we got this one does at this speed, this mile per hour. But then we went to look at that on actual deployments. We found there was a big difference. So even though we are getting these drag coefficient forces in a wind tunnel, when we applied them to reality, we are getting different results. Like one with a lower drag coefficient might have been more effective getting the bag out of the container because its initial shock force was higher. So there's all those things we take into account. So we don't just look at what happens in a laboratory or calculating the drag coefficient of a canopy. There's one manufacturer specifically that does that all the time. And he gets on forums and keeps on saying, oh, I have a drag coefficient of this. What does that mean in reality? What does that do for me in my container? Does that maybe create too much? What we have seen is we created some really high drag pilot chutes, and we had some of the worst reserve openings. They were horrendous. The shock forces, we were getting 16 and 17 G opening shocks on these canopies. This is, if you're at terminal velocity and you get 16 or 17 Gs, that's going to hurt you. So creating too much drag is also a problem. And the other thing was creating too much drag, it's canopy damage. We just did a series of test drops with another pilot chute design that we were looking for, not for our Skydiving, but for our bundle systems. And we were seeing it was tearing those bags apart, the lines were coming out, the safety stoves were breaking. So it's not just a number that we applied in a formula to the equipment. The testing is really where it comes in. Did that answer your question?
Yeah, you seem to talk a lot about timings, but not much about actual forces and with the dynamic corners that you talked about.
Yeah.
It seems like that.
Well, okay. So what do we want with dynamic corners? We don't want to take it more than the only thing with dynamic corners on getting the reserve bag out the container is that the pilot chute has to create more force than the dynamic corners hold that bag in. So when you take a scale and you say, okay, I'll use the example. It took me 15 pounds to get this out of the container. And these things are slow. It's not out in reality on a skydive. And then we see that at this speed, our pilot chute would create 18 pounds of force. That's enough. It exceeds what's in there. It has to exceed it. There's no magic number that says it has to exceed it by 20% or 30% or 40%. And actually what you'll find in the static test, we do these tests on the ground. We do a lot of tests on the ground with scales. And when we go when we actually do them in the air, the dynamic corners are less effective. And it's because your body the rig molds to your body and so on. So bench tests historically have been unreliable. I'm sure you guys have seen history of bench tests, containers locking up. I think the French Federation about 10 years ago did a whole series of tests with all containers, and they published this stuff. And I think about 80% of the containers at some stage with these bench tests locked up. It was a loop trapping through the grommets. But those same containers were being jumped every day, and reserves were fired every day, even with AEDs, and people weren't dying on them. So that's why we've got to be very careful about information we get from a bench test. And that's why we finally have the tools to take all the stuff we do at bench tests and put it in the air with these load cells that we're getting. So at the end of the day, we might get nothing from all these tests, but or we might have some real numbers that we can give to the jumping public. It says, this is ideal, this is what works for this. It's not going to be for every container. This is what works for this container. So this is a force. These container manufacturers, we're giving that to them as well. They can take this information and possibly improve their designs. Or we might find that there's nothing wrong with any of the containers on the market. Now we have to go to the AED manufacturer and say, here's the proof. We see that all these containers are working. Now we've got to look at what's happening with AADs. Do they need to be fine-tuned? Do we need to raise altitudes? Do they have to get a better method of in the algorithms of determining the altitude they actually fire at? Because we don't know. The firing altitude is a virtual altitude. It's not a real altitude. Any more questions?
Only a stupid one, but why is the firing altitude not the real altitude?
Because it's just based on air pressure. Okay, so the air pressure varies so, and it's on your back. So you have this massive. You saw those red lines that were going up and down. So it determines when it fires, and you'll see that it gives you a number. It fired at this altitude, but it was the pressure that it fired at when it was on your back was at that altitude, which is not the real altitude you're at. So if you're on your belly, it's going to be most probably 260 feet lower, because that's the rough estimation of the burble creates a 260 feet variation. But there's so much happening out there that it's very difficult to actually, and I mean, I take my hat off to what these AED manufacturers have done. They've got a very difficult task ahead. But the only way we can get a true altitude is if we had a infrared altimeter. What's the one that they use in the military that they can tell exactly, that measures the ground distance from where they are?
Radio.
Pardon?
Radio altimeter.
There we go, you got it, sorry.
What does that mean for you set your AAD for a certain altitude? So when can you believe?
Okay, now the altitude you set it is the virtual altitude. It's already taken into account that 260 feet.
What's the highest it could be based on what you said?
Okay, so if I don't know what AED you have.
Cyprus.
Okay, so, and I guesstimate that, and you can speak to them and say, what is that variation you use? Because this is the thing you need to take into account when you move your altitude up. So it's, right now it says it fires at 750 feet, right? So it has a true altitude that it's actually looking at, the pressure altitude. And it's probably, based on what we know, it's about 1,000 feet. And I mean, they're here, you can ask them. So if it's at 1,000 feet, you know that now you want to move it up. So you move your 750 feet to 850 feet. Well, now you're at 1,100 feet. And that's the altitude you should work at when you determine how high you're going to open your main canopy. Because when you're standing upright, it's going to read closer to real altitude than when you're on your belly. So if you're sniveling your main, you pull it 2,000 feet and you start sniveling to 1,100 feet, your AED is going to activate. Does that answer the question? And it wasn't a stupid question. I mean, this is the big problem with people, and why some manufacturers don't want to push it up, because people don't realize that the AED doesn't really fire at the altitude they say it is. It's actually higher than that. But in true, and it is very dependent on your body position.
Or lower.
I think most AED manufacturers work that they said, based on when they designed their system, the way skydiving was at the time, that was the lowest altitude it could fire at. So when they say 700 feet, they believe that's the lowest altitude it can fire at. But it can't fire higher than that. Okay. But it was based on that, what they came out in the late 80s. So based on that, things have changed, and that's one of our arguments with the AED manufacturers. Not arguments, it's one of our discussions with the AED manufacturers. You base this on discipline there, and you haven't changed it since then. Maybe they have changed it in the algorithms, I don't know. But I know that the more modern AEDs automatically have a higher set altitude. The ones that have been out since then.
Thank you.
Yeah. Was this informative? I don't know. Okay. Well, thank you.